Okay. The first talk is from Professor Francesco Bruscioni, roadmap of the quantum computing in South American context. Oh, by the way, my name is Yi. I'm also from Stellenbosch University. So just a brief introduction of myself. So yeah, first is Francesco.
Okay. Yeah, thank you very much. I assume that you can hear me. Yeah, thank you. So thank you very much to the organizers for having me today, and I'm sorry that I can't be there in person for various reasons. Yeah, but it's nevertheless very good to have an opportunity to address you at this edition of the CHPC conference about what's going on in quantum computing in South Africa. Just not to jump too much and too quickly in the cold water. Yeah, let me start with some generic remarks that I've probably done already a million times. Yeah. What we are experiencing now on a technological side since the end of the last century, yeah, is that two of the most prominent theories and technologies of the last century are coming together, yeah, and that's essentially information science and quantum mechanics, quantum physics, yeah. And these two disciplines merge, yeah, to form what some people call quantum information science or quantum information processing and communication. There are various labels for this merger. Yeah? But anyway, the three biggest pillars of this new science, yeah, are quantum computing, quantum communication, and quantum metrology. Yeah, quantum sensing. Yeah. And of course, there are a few other applications like quantum biology, but they could all, for one way or another, fit in one of the three pillars if we want. Yeah. But these three pillars, their ultimate goal, yeah, could be seen as giving us the next generation internet, yeah, a fully quantum internet in which the computing, the communication, the measurements, everything is done according to quantum physics. Yeah, so that's a little bit the generic picture. But I will speak now only a little bit in generic terms about quantum computing, and we can leave communication and metrology for another occasion. Yeah. Let me start with the worst case scenario. Yeah, the worst case. If you look, these days you open the TV, open a newspaper, Google around 5 minutes. There is something about AI and ChatGPT and so on and so forth. Yeah, and all of this would not have been possible without the serious improvement in our computing hardware. Yeah. Without GPUs and TPUs, we wouldn't have the machine learning capabilities that we have today. Yeah. And in this arena, yeah, there is now also the quantum processors. Yeah. And we know already that some current available quantum computing processors are already very good at solving certain tasks, for instance, for machine learning, estimating kernels and things like that. Yeah? So that the worst case scenario for quantum computing is that in the array of from ASICs to CPU, GPUs, and so on and so forth, there will be also a little quantum device able to do something. Yeah? But of course, the ultimate aim is to have a universal quantum processing unit. Yeah, but we are still a little bit far away from that, as we will discuss just now. So, the other topic that we all probably can't hear anymore is the fourth industrial revolution. Yeah, and some of the aims of the fourth industrial revolution will only be possible if we bring together this second quantum revolution that we are experiencing now with the aims of the fourth industrial revolution. Yeah, because what quantum technology promises us is through metrology to give us probably the best data collection and the most precise data that we ever measured. Quantum communication promises to give us really secure data transport, yeah, based on physical principles and not on mathematical complexity. And quantum computing, we know, will be good at solving certain classes of problems. Yeah. There is, of course, quantum computing goes back maybe to the 90s, yeah, where some pioneers like David Deutsch and Richard Jossa came out with first, now we would say, relatively simple algorithms to show that in principle, quantum computers, if we had one, could solve some problems in a more efficient way than classical computers, yeah. And this kick-started, of course, a search for many more algorithms, yeah. And probably one of the biggest breakthroughs, you see it in red at the bottom left corner of the slide, was the famous algorithm by Peter Shor, yeah, in which he showed that there was a significant speed up on for a quantum algorithm to factorize large numbers. Yeah? And as you know, that is a threat to our current cryptographic schemes. Yeah? So because those rely upon not being able so easily to factorize large numbers. Yeah? So this, the fact that not only play algorithms could run on a quantum computer, but also really serious stuff, yeah, with potential huge implications for security and everything, yeah, really kickstarted the boom for search for algorithms. Yeah, and in the meantime, the algorithms from linear algebra to machine learning to optimization to chemistry simulation, all possible sorts of algorithms are available, and there is no end in sight. Yeah. Computers are only as good as the algorithms that run on them. Yeah, it's not only a matter of improving the CPU. You need also to invest some time in improving the algorithms. Yeah, so that's what many people have done since the 90s. Yeah. So, and in the meantime, the on paper, yeah, the advantage of quantum algorithms is that they give you a speed up. Yeah, for instance, one can show that the Grover algorithm, which is an algorithm for search in unstructured databases, gives a quadratic speed up on the traditional search algorithms, which is not bad. Yeah, but then you see also in this list that on the side in the column on quantum algorithms there are lots of logs. Yeah, and that means that there are algorithms that can give you even an exponential speed up. Yeah, for instance, in linear algebra. For eigenvalue solutions and other linear algebra problem, matrix inversion, and so on and so forth, you can really show that quantum computers will be able to give you an exponential speed up. Yeah. Similarly, also, machine learning is also mainly based on linear algebra. Yeah, so that there's potential for large speed ups there as well. Yeah, everywhere time you see a log, that's a good sign. Yeah? Anyway, as I showed in the timeline of quantum algorithms, the business started in the 90s, yeah, and many countries, many nations jumped on the potential of quantum technologies in general and quantum computing in particular, investing huge amount of money. Yeah, also many companies, some of them probably sponsored the CHPC conference, invested large amounts of funding to build quantum computers and to develop the software to run on them and so on and so forth. Yeah, I'm speaking here billions of dollars. Yeah. South Africa has been a little bit late on jumping on this train officially. Yeah, unofficially, there were always a handful of us in South Africa working on quantum computing, communication, and sensing. But it's only since a couple of years, since 2021, essentially, that DSI has formally approved a quantum technology initiative that in a colloquial way we call SAQT. Yeah. And SAQT at the moment is a consortium of 5 universities, WITS, Stellenbosch, UKZN, the Cape Peninsula University of Technology, and University of Zululand, and the Cape Peninsula. Sorry, I already mentioned the Cape Peninsula University of Technology, sorry. Yeah. But you know, the aim is to make this consortium bigger and include many more people to work on these things. Yeah, we have a website, saqt.org, that you're welcome to visit, and on that website you will find also this official document that summarizes what we're planning and intending to do. But in a nutshell, you know, the aim of the quantum technology initiative is to improve to educate people in quantum technologies and quantum computing, and to build a critical mass of experts and users. Yeah, because that's what we need. Yeah. And probably, you know, the more ambitious aims of the quantum technology initiative is, of course, to create the environment, yeah, for quantum technology for the use of quantum computing to start in the country. Yeah. And that implies also that we start and initiate discussion with the local industry, maybe even come up with our own startups, yeah, that try to solve some problem using quantum computing. And of course, we need to interface with the other technology platforms in the country, because, you know, you can use quantum computing essentially in almost every other disciplines in which you use high performance computing. Yeah. And recently, together with Andrew Forbes and Philip Roux, we wrote a little article on summarizing a little bit the intention of the quantum technology roadmap in a more concise form. So these are some of the but probably, you know, at this stage and moment in time, the most important aspect of this is the training and the creating of a critical mass of users. Yeah? And for this reason, we have also partnered with QWorld, yeah, which is a non-profit organization that offers quantum computing training, essentially mainly online. Yeah. And we already had one event. We have now, I think next week, we have a second event. I think it starts this weekend. Yeah. For the first event was Q Bronze, yeah, in a kind of Olympic sense, starting with the bronze medal. Now this weekend we have the start of Q Nickel, which just goes one step further. And everybody is welcome to register and participate. Yeah, and we will continue. In the first event, we had hundreds of students and interested people taking part, and we hope that we will repeat the success of that. Yeah, I think I'm only sorry, just checking quickly the time. Okay, I have only 20 minutes. I already spoken 11. Yeah. So let me maybe in the remaining 5 minutes, just to leave a few minutes and maybe for questions, try to tell you a little bit where we are, yeah, and what we can realistically hope to do with quantum computers in the really near term. And near term, I mean a generation of PhD students, let's say 3-4 years. Yeah? So there've been lots of talk of quantum supremacy, quantum advantage, quantum practicality, quantum utility. Yeah? And it started a few years ago when Google and NASA published the first paper claiming that they have shown quantum supremacy. Yeah? And the claim was that for a relatively artificial problem, the quantum computer was able to solve this sampling problem in a few seconds, and it would have taken a classical computer many, many years to solve the same problem. Yeah. So this was the first claim of quantum supremacy. There was, and now you see just a few months ago, IBM published a paper where now they claim quantum utility. So you see, from supremacy, we scale down to utility. Yeah. And what is really very interesting is that it didn't take too long, yeah, for the classical computer, yeah, using quantum-inspired algorithms to fight back, yeah, and shows that even these problems are in the range of usability, approachability of classical computers. Yeah, it just took a few weeks of of work to achieve that. Yeah, which shows that how difficult it is really to claim real advantages. Yeah, it's a healthy competition between quantum and classical. Yeah, in which I mean, we know who will win at the end. Yeah, but it's there's still lots to be done. Yeah. Another term that maybe is probably the one that I like most. Yeah, is the quantum practicality aspect of things. Yeah, because we don't just want a quantum advantage on paper, where we know that in principle, if we had a perfect quantum computer, we would reach a perfect exponential speed up. Yeah, we need to do what we can do now. Yeah, and quantum practicality means essentially the look for those applications that in which we have a realistic chance in the near future. And near future is, let's say, a PhD generation or two, yeah? To outperform a classical computer. Yeah? And there's a very nice paper by Matthias Troja from Microsoft and some of his colleagues where they do a very nice comparison, yeah? between what relatively standard, maybe a better NVIDIA GPU with an investment of, let's say, roughly $10,000. I don't know exactly what the latest price is for them, yeah, can do, but something that you can buy today and you can run today, yeah, if you want, compared to a quantum computer that has 10,000 logical qubits, yeah? and fairly reasonable gate times and so on and so forth. Yeah, the best we have these days, and I think it was announced a few days ago by IBM. It's a quantum computer. I think the name is I think it's Condor, if I remember correctly. Sorry, it's just a few days. Yeah? That has roughly 1,000 odd qubits, but those are not logical qubits; those are physical qubits. Yeah, so they're not error-corrected qubits. Yeah, maybe they're error-mitigated qubits, but they're not really error-corrected. So this is a, assuming that we can double the number of qubits every year, and assuming that we can convert physical and logical qubits, it will take probably another 2 generations of PhD students before we have these 10,000 logical qubits. Yeah. So this is something that we don't have now, but it's just a nice comparison. Yeah. And what emerges immediately, yeah, is that quantum computers at this stage, yeah, and this ideal quantum computer that we don't have yet, yeah, that we might have maybe down the road in, let's say, five years or so, yeah, is that there is a big bottleneck, and that is the input and output bandwidth of data. Yeah. So on a GPU like the one that I mentioned, you can input data at thousands of gigabits per second. Yeah. On a quantum computer with the parameters specified above, if you can reach 1 gigabit per second, you are good. Yeah. So there is a so that at the moment, yeah, we can already say that quantum computers will not be very good at processing large amounts of classical data. Yeah? So it's the inputting of classical data into a quantum computer that is slow. Yeah. So that and now maybe okay, let me come to the famous statement, because I'm running out of time. Yeah. So that if you're looking for practical uses of quantum hardware that we have now, and let's say in the next PhD generation, we should focus on problems that are kind of big compute, yeah, problems that have small data and large computational power, yeah, and not big data problems. So probably in the next, our next generation of PhD students will not significantly improve transformer models on quantum computers, yeah, mainly for this one challenge that is the inputting of classical data into the quantum computer. Yeah, I will skip maybe now a little bit these technical problems, because I think I'm running out of time. Yeah, so that my recommendation, yeah, and that of others as well, of course, yeah, is that if you have new PhD students that are looking for a quantum computing challenge, let them work on simulation of quantum systems. Yeah, let them look into quantum chemistry simulation, material science problem, and cryptanalysis is also one of these. Yeah, if they are interested in quantum machine learning, that will be mainly probably a theoretical enterprise, yeah, because there is not much realistic hope, I think, at the moment that you know, in the next couple of years, quantum computing will be able to outperform the large language model that we all like to use these days. Yeah, so that it will come, but it will require the hardware to improve significantly. Yeah. So in a nutshell, since now it's 19 minutes, this is what what I wanted to say. Maybe just conclude with some you know, some possible interesting use cases, yeah, where we could that emerged from a big study in which I was involved, to identify some problem. Yeah, for instance, new carbon capture materials. Yeah, that's a big computational problem where hopefully quantum computers will assess, help us assess, or antibiotics in wastewater, fertilizer productions. Yeah, eco-friendly fertilizer production is a big problem. Producing fertilizer is expensive, yeah, and in terms and requires lots of effort, whereas bacteria do it for free. Yeah, but we don't really know how. Yeah, so that what we need to model and understand. Yeah, and of course, in the context of climate change, yeah, is how do we make sure that we will keep feeding the many billions people on our planet? Yeah, because climate change will induce certain agricultural areas to move, yeah, from one part of the world to another one because of the varied climatic conditions. Yeah, and that will require a huge logistics problem. Yeah, how do we keep up the production of food in a changing world? Yeah, and okay, other vaccine problem and so on and so forth. So, but now it's 20 minutes, so thank you very much for for listening to me. I'm not sure if you have questions or if you have time for questions. Yingxia, you will tell me.
For quantum computing and how we are working with the DSI and the CHPC and other industry partners to further quantum computing research and get it funded. I'm going to go through these initial slides very quickly because they're mostly intended for people who don't know how the scientific process works in South Africa. It follows from the National Development Plan, where science has been put in a position where it is being used to try and solve some of South Africa's problems, such as getting us out of poverty, reducing the income gap, solving some of our bigger problems. And as part of that process, every couple of years we have the scientists and industry partners come together and I try to identify what the problems the country has, and then we'll get published as our white paper. And from that white paper, they then take the content in there and they try and they build that into a policy framework document, which is the innovation plans. These policy documents are they don't specify what science has to happen, but they do guide scientists as to which technologies they should be, or not which technologies, but which problems their science should be attempting to address. Sorry, just give me a second. The policy documents get updated from time the reason for this is obviously the world changes, the technologies change. You get new technologies, ChatGPT is an obvious example. Machine learning evolves. Quantum computing is an example of this. And we have tried to also keep those policy documents in sort of 10-year or 5 to 10 year chunks, because you don't want to be doing research and then dropping it and changing rapidly to other research. You need your researchers working on projects for enough time to actually make a difference. I think I covered some of this. They're not implementation plans. They're just point researchers of what they should be covering. What I do want to cover in this particular decadal plan is the fact that there are 5 main focus areas. There's modernization of agriculture, manufacturing, and mining. There's exploitation of new sources of growth. There's innovation problems in health and energy. Health and energy is quite an emphasis on at the moment. Trying to support a capable state, and then addressing major societal changes such as climate change, education, future of society. In terms of quantum computing, there are quite a few applications in the 4-hour space in terms of, and it's a very buzzwordy term. The things that go under there are things like robotics and AI and computing and items like that. We see ourselves in the CSR as aligning with some of these targeted programs such as health and energy with the quantum computing space. So just who the CSR is, for those who don't know, well, the Department of Science and Innovation is made up of these companies. The National Research Foundation and the CSR are tightly aligned, and I work for CSR, which is basically South Africa's primary science research institution. My particular unit, which I mentioned at the beginning of the talk, is this one in the bottom left, the Next Gen Enterprise Institution. The reason we are playing in the quantum space is because the unit specializes in computing and ICT. ICT is a bit of a buzzword, but it's basically satellites, communication technologies, and computing. You'll notice on this page these are clusters, other clusters within the CSR, that these clusters actually align with the National Development Plan's targeted problem areas. And in particular, my unit is specifically focused on e-government and 4IR technologies, amongst other things. We initially were proposing to the DSI that we need to get education as a primary target in the quantum computing space, and that we can't actually wait until the computers are here before we educate people. It's a little bit like giving a programmer a new programming language to learn and then expecting them to be experts without the time and energy and expertise to train and learn and actually use them. Often when you train a programmer, they've got to spend extra time while they're actually implementing programs to get a little bit of experience. There was a document that came out from the Quantum Working Group, which is a work in South Africa. It's a group that was formed between all the universities and various stakeholders that specifically started prioritizing and was sent to the DSI to give them a framework for what we needed to prioritize in terms of quantum stuff. And the items listed on this page are the primary areas that were recommended. And CSR is now very much working in line with this quantum working group paper. Specifically at the moment in education and training programs, but also the quantum groups can't work in isolation. There are quite a number of groups, but they're reasonably small, and we will be able to make much more progress if we're working together as a unit. We specifically mentioned to the DSI that they needed to prioritize training for staff, they needed to upskill research chairs. Again, this is in line with the Quantum Working Group document. You need research chairs to teach people and getting skills on all levels is important, particularly on the upper levels, which can then pass skills down. I want to talk a little bit about the executing the flagship programs. One of the advantages that the CSR has is that we have all of these various units. We've got chemistry, we've got units that deal with chemistry and manufacturing and alternative energy and health, etc., etc. And our unit is uniquely positioned in a space to connect those, to find out what problems those units have that would be advantageous to try and solve on quantum computing. And in particular, there are problems in South Africa that international quantum researchers are not going to look at. The example off the top of my head is we have South African-specific strains of HIV, and to be able to throw quantum computing at that kind of problem would be very useful. The CSR is also very intent on driving product research, making them practical and putting them out into industry. So, for example, we're working with other industry partners and IBM at the moment to try and find practical applications for the computers as and when they mature to the point that we can do things with them. This slide was mostly just to give an example of what companies overseas are doing with quantum. They're using anything on the automotive industries, batteries, chemistry problems, optimization problems, biology. That's not an extensive list. I don't know how much time I have left. Specifically, the main industries that we've identified up front that we want to do more research into this is we can definitely hook into renewable energy, health, because that's a big part of the data plan, modeling data processing, chemistry, etc. We did have, these are the main universities in South Africa that are busy, that have quantum computing groups and have access to quantum computing computers, but they had access through IBM and Wits University to the machines. That access has unfortunately been removed, but the CHPC specifically is looking at trying to host new quantum rings for the universities. This is just to give you an idea of some of the companies overseas working specifically with quantum. There's some big names in here. There's NVIDIA, Intel, and Microsoft. I won't go through all of them, but and it goes quite a bit bigger than this. So in South Africa, we really need to get with the program if we want to keep up with international researchers. I think the microphone just went off.
Yeah, it's on. It's on.
Maybe it's too close.
Sorry.
Take problems. So just in summary, we know that the quantum hardware manufacturers have been doubling the capacity of the quantum computers. They almost double the capacity every year. In fact, there was an independent that announced a 1,000-qubit computer last week, and just yesterday I saw an article from IBM advertising a quantum computing chip that can be sort of connected with each other so it can scale. So that's going to be very exciting to see when that happens. We do need priority access for the available quantum computers, and that is in progress at the moment. And and that we just continue to work with the industry partners and the other quantum computing groups to coordinate efforts that align with the technical plan. I covered some of these. We did indicate you need a few hours of training. The DSI has instructed us that they also need to know how to measure the success of any quantum program, and we have a little bit of a difficulty with this at the moment because the main way you show success is actually building a prototype. And we're in a bit of a chicken egg problem where we need the funding to build the prototype, but we need the prototype to get the funding, so that's a little bit of a problem. But yes, we're making progress, and it is on the DSI's long-term plans to scale up and align with these goals. And that's the end of my. I don't know if there's time for questions.
Well, thank you so much. Any questions from the audience? Yeah, there it is.
Hi.
Hi. Yeah, I'll just shout it away, it's fine. Thank you very much. Well, really interesting work, and I'm glad CSR is getting into this space. I'm just quite curious, with the hardware evolving so fast, where do you think the main focus is going to be in the next few years? I think Francesco touched a little bit on it in his talk as well. Are we going to be looking still very much at sort of theoretical algorithm development, or are we going to be actually getting into the hardware design, or kind of a bit of both?
I don't think South Africa is going to go into the hardware design at the moment. The CHP is looking at hosting. My unit is looking at trying to roll out some of the issues. There's a lot of, if you look at some of these software development kits for quantum, you will find there's a lot of optimization problems, a lot of pattern searching. But at this particular moment, we are working still with what they call RISC devices, multi intermediate quantum, that are not big enough to fully test those. But the fact that a lot of these software libraries are prioritizing chemical problems and search algorithms is an indicative of the way it would be useful. We really would like to work with the other units with the CSR to find out where the big problems are, where the big data problems are, and connect that with the working groups and industry to try and produce something.
Okay, so on behalf of all organizers, I give a small gift.
Oh, that's sweet.
So you might speak.
Cool.
Okay. Okay, so please, now we move to the third speaker, Kevin Fufu. And please.
Thanks. Good afternoon, everyone. My name is Kelvin Fufu. I'm a researcher at the CSIR, and our group does biophotonics research, and we've been using machine learning as part of our research, and we've decided to kind of jump on the bandwagon of quantum machine learning, and so we've been doing some work testing out. So some of the work we've been doing that I'll talk about later is basically we've been looking at the comparison between classical machine learning algorithms and quantum machine learning algorithms applied to some data sets. So I'm just going to run through a bit of quantum computation work, some quantum computation ideas. Then I'm just going to quickly talk about the work we did comparing the performance of quantum machine learning algorithms and classical machine learning algorithms. algorithms. So some of this will be kind of a repetition of what the previous speakers have mentioned. For instance, there's a big race for the development of a fully functional quantum computer or fault-tolerant quantum computer, and there's a wide range of companies that are looking into that. The European, there's a large European quantum startup landscape where you have a lot of companies doing developing hardware and software technologies. So you might be wondering what a typical quantum computer looks like, and there is no such thing as a typical quantum computer because there are a wide range of architectures that you can use. For instance, the Chinese have a 76-qubit photon-based quantum computer. You can also have an ion trap quantum computer, like the one with high-voltage ion Q8, which is a 32-qubit quantum computer, and IBM has a 53-qubit superconductor-based quantum computer. There are a lot more, but these are just the examples that I found. So the critical difference between quantum computers and classical computers is that classical computers work on a bit-based system, whereas quantum computers use qubits for information as the fundamental unit or used for information processing. There are significant differences between qubits and bits, listed above. So another key difference is that if you've worked, I don't know if you've worked in maybe the electronic space, then you probably recognize some of the classical gates which are used for classical computing, such as the NOT gate, the AND gate, the NAND gate, etc., etc. The quantum equivalent, there's the quantum equivalent, the poly gates, poly Y gate, poly X, Y, Z gates, the Hadamard gates. These are a wide range. This is like the wide list of gates that you can use for quantum computing applications. It's not exhaustive, but just to give you an idea. So some useful terminology in quantum computing. You can have something called entanglement. Entanglement is a special type of correlation that exists in quantum systems, or non-local entanglement at least. So you cannot get non-local entanglement in a classical system, and it's quite useful for computational applications, and it's been shown to give an enhancement in quantum computers which you won't possibly find in a classical computer. You can also have superpositions of states. So a superposition is basically when the system exists in two or more states at the same time. It's not you can't have a superposition of bits, but you can have a superposition of qubits, and this gives quantum computers a type of computational advantage as well. So I just added this to kind of refresh on the definition of a quantum computer. And a quantum computer is a computational device that uses principles of quantum mechanics to perform computational tasks. And as quantum computers continue to develop at the moment, a lot of researchers are looking for applications for quantum computers. Some general advantages that you might find is that having a qubit-based system can increase your storage capacity and can allow you to do more parallel computations. So quantum computers have a wide range of application areas, and this includes optimization, cryptography, machine learning, data analysis. So the big area would be optimization tasks, because for particular optimization tasks, quantum computers are more suited to solve certain optimization and cryptography tasks than classical computers. So just a list of common algorithms in quantum computing. We have the Deutsch algorithm, which was one of the earliest algorithms which displayed the ability for quantum parallelism. The Grover search algorithm, which allows you to search an unstructured database. Shor's algorithm, which allows you to factor large numbers, which is a big problem for classical computers, which is the reason why our banking systems are quite safe at the moment. So Francesco showed some of these speed-ups, particularly he showed that for search algorithms. For instance, with the Grover algorithm, if you have an unstructured database, you would need up to the order of n steps classically in order to search for a particular item in your database, whereas the Grover search algorithm would be able to do this in order of square root n steps. Say for instance, if you had an unstructured database with 100 elements, with a classical algorithm, you would need an order of up to 100 steps, whereas with a quantum Grover search algorithm, you would need around 10 steps to search such a database. So the term quantum machine learning is quite broad and quite extensive. So just to kind of summarize what people might be talking about when they're talking about quantum machine learning, for instance, you might have your input data might be classical or it might be quantum, and so your input data might be classical, and your machine learning algorithm or your classic quantum. In that case, that's a quantum. That falls under machine learning algorithms. You can have a classical quantum data source, which you run on classical computers. Some people refer to that as well as it falls under the bracket of quantum machine learning algorithms. And lastly, you can have a quantum data source and a quantum algorithm that also falls under the bracket of quantum machine learning algorithms. So in the work we did for the project we were working on in our group, we took the Skycade's breast cancer dataset, and we wanted to make a comparison of the performance of the quantum machine learning, rather a quantum enhanced machine learning algorithm and classical algorithm. So one of the algorithms that we looked at is the support vector machine. The support vector machine works by just generating a hyperplane, an optimized hyperplane that effectively separates your dataset into different classes. So it's quite simple to work with when you have a linearly separable dataset, but once you don't have a linearly separable dataset, then you need to perform a few tricks, and the trick being you need to do a feature map. A feature map basically means you take your dataset from the Rn space into a higher dimensional space. For instance, so in the context of quantum computing, in our case, we looked at kernel-based methods. So what we do is we take our data, which is in the Rn space, and we map it into the Hilbert space, which conveniently has a nice distance measure embedded in it, which is just the inner product. So for our work, the classical kernel that we compared with was the radial basis function kernel. Then for comparison, we took our data set from Rn space, mapped it into the Hilbert space using a feature map called the ZC feature map. You find it on the Cascade site, and then using the ZC feature. Once we've encoded our data in the Hilbert space using our ZC feature map, we then just take an inner product measure as our distance, as our kernel measure. So again, we also looked at another classical algorithm known as the k-nearest neighbor algorithm. This one was much simpler because it just takes distance. It generates, your algorithm basically generates a range of classes, and when you introduce a new point, it just looks for the new point that is closest to it looks for the class which the new point is closest to. So classically, you can use a Euclidean distance measure, you can use a Manhattan or Minkowski distance measure. For our work, we just basically took our data set, we mapped it into the open space, then we defined a new distance measure, and we ran comparisons. Then lastly, we used an artificial neural network as well as a variational quantum circuit to perform the classification task on our scikit data set. And okay, I'll just skip. These are just details of the neural network. So what I wanted to get to is the results that we got from 4 different algorithms. So for the work that when we were doing the classification, we found that our classical algorithms outperformed our quantum algorithms, not just in terms of accuracy, but in a range of other metrics as well. And another thing that we noted was our quantum algorithms were taking significantly longer to perform than the classical algorithms. For instance, with the artificial neural network, it took around 33 seconds to classify our data, whereas it took around 632 seconds with the variational quantum circuit. With the k-nearest neighbor algorithm, with the classical version, it took 0.21 seconds to do the classification, but with the version where we use the quantum kernel, we get around 495 seconds. So this just kind of led us to start to question where can quantum machine learning algorithms be advantageous, and we came up with a few areas where possibly we could have an advantage by using quantum machine learning algorithms. And these are areas where your data is quantum in nature, and they also have to consider very high dimensional data spaces where, like Francesco mentioned, you should be able to kind of like, if you have a way of quickly encoding your data set from the classical from the classical space to the Hilbert space, then maybe you can, if you have a high dimensional space, then you can have that advantage. And in particular, optimization problems where you clearly cannot use a classical computer, you just have to look for other needs. So some of the limitations for our study was we didn't do hyperparameter optimization, and this was because whilst it was easy to do on the classical algorithm, it proved a bit more challenging on the quantum algorithm because you also need to optimize on the ZZ feature map, the circuit of the ZZ feature map. So it kind of scales, like how the number of parameters that you need to optimize also scales. And another limitation was that instead of running our algorithms directly on the IBM quantum computer, we were forced to use the simulator. And this, we already know that if we run it on the actual quantum computer, there will be losses which will worsen the performance of our quantum algorithm. So yeah, just to summarize everything that we did, we wanted to compare the performance of our quantum machine learning algorithms with the classical machine learning algorithms. We found that whilst quantum machine learning algorithms might be good for specific tasks. They are not generally good for tasks where your classical computer is good. And this is because there's the encoding process which makes the whole process a lot slower than what you would be able to do with a classical computer. So if the problem is completely solvable classically, there is no real purpose of using onto the computer. And for future work, we're looking to try and optimize our quantum algorithms just to see if we can get something. And I'd like to acknowledge the CSIR and DSI for funding for this research. Thank you.
Time for one quick question. Okay. If not, then we just a small piece from the audience. Thanks, speaker. Okay, you're a lot person, maybe you can start.
Yeah, okay, I will rechart it.
Okay, so,
welcome, thank you for not inviting me, but allowing me to talk to you guys today. Microphone, here we go. So, I'm Scott Woodley, I'm based currently in the Department of Chemistry at UCL, I'm the Director of the Hub, and I'm also the PI of the Materials Molecular Consortium, not to be confused with the MMC based at Limpopo. So basically I'm a material scientist. I've done most of my career on structure prediction, and that's build clusters, solids, and also look at solid solutions, and that's the material problem I'm going to try and address today. But I should really be honest and say, look, I usually use classical machines, standard CPUs, not quantum computers. So that's me standing in the tray beside Archer 1. Below there is Archer 2, this is the national supercomputer in the UK. And the other machine over there is the machine that I run at UCL. And I should say that machine there, the electricity bill costs me £800,000 a year. Pretty expensive. You need to times that by 20, well, how many rand it was. So essentially I'm used to running classical computers, and I'm going to try today and explain what's my take on using a quantum computer and what we've attempted to do to solve structure prediction problems. Before going there, I should say that the money is all coming from a project called Excalibur, and I would like to introduce the PAX Excalibur project first, before continuing on the QBET project. So what is Excalibur? I'm proud to say that the UK finally has got their act together here and actually is funding all these different areas. You go on this website here, you can find these boxes. It's basically the Research Council of the UK, the Met Office, which is the Weather Boys, and the Fusion Energy Technology group have come together. We're trying to make sure that we're ready that when we switch on an exascale machine in the UK, we have the software, it optimises scales, we have the people skills as well, which is very important. And all these different areas, so I'll just look at one of them. You go to the website, you click on these. Cross-cutting area, for example, all these different areas here, there's a project running currently. One of them is led by Peter Coveney on validation, verification, uncertainty, quantification. Peter Coveney's CV project at UCL. The other one I'm involved in both these, is led by Viv Kendon in Strathclyde, and this is basically trying to see whether quantum computers can use as accelerators to accelerate our calculations run on an exascale machine. And that's what I'm going to cover in a second, but like I said before, I'd like to introduce the PAX project, because in the area that's high priority use cases, I've led a project where I've brought together, in the red dots is where all the people for the MCC are based, and the yellow dots another head consortium, UKCP, that's Carl Polinova. And this group of researchers were all interested in understanding the mechanism of predicting properties and reactivity of materials. And typically these materials are of an order of length scale of centimetres and time in seconds, but the physics that underlay determines these properties are on the length scales of angstroms 10 to minus 10 meters and picoseconds. So you can see there's a huge problem there, and we are trying to optimize the energy as function of particles. When we ran this phase mod, where we're trying to work out what do we need to do to make sure we're ready for exascale, when we switch that machine on, we discovered there are other people doing similar sort of problems and have similar, well, different problems completely, as you'll see, but they have similar underlying problems in terms of scaling up, because they also have algorithms based on particles. And so here is what we did. We brought together people also now, the engineers that are trying to have water droplets, well, they're modeling water droplets hitting the sea fences, they're trying to model sea fences. We've also got cosmologists that have particles that are pretty big to make planets. They also have particles that are galaxies and trying to do the Big Bang. So there's 20 different co-investigators, they're all listed there in these different areas, project partners on the bottom. And essentially we all have the same problem. How do we scale our calculations up? And we're all particle-based rather than finite mesh-based. So there's three types of calculations we're looking at. It's high throughput calculations. You've got lots and lots of small samples that you're trying to run across the whole machine. We also have the hero calculation. We want one calculation to run across the entire machine. And we also have complex workflows. For example, we might have two quantum mechanical regions embedded in atomistic modeling. And so this is a slide that we presented at the last exascale meeting just last month, just to highlight some of the things that we're trying to do, trying to create APIs of our codes, and this is a hard problem, trying to create software libraries that fit lots of different software. Parallelization, one of the things we're looking at is task-based parallelism. For example, integrals of s orbitals, p's, d's, are more expensive the higher up you go, to try and do load balance across the machine by doing task-based parallelism. And we're also, I didn't announce, but you may have heard that the UK are going to swap, they're going to build two more tiered one machines in the UK based on GPUs, one for the AI boys down in Bristol and one based next to Archer 2 in the north for the more traditional people. So we need to get our code supported to GPUs. You can see many codes are ported, but there's still many different problems we have. Portable software standards only give access to a subset of hardware capabilities. And there's an important thing about memory layout. Is it array to structure or structure to arrays? But anyway, I need to move on to the actual topic, which is quantum hardware, what I've been doing. So I've led a work package for materials problems, and there's a qubit project, and the hardware goes on and off. So this is the hardware. It's a quantum annealer. Essentially, you're probably more expert than I am here, but my take is we have these qubits. The strength of interaction with the qubits is controlled by magnetic fields, and you basically start this thing off where it's just random qubits, and as time evolves, they'll settle down and keep in the ground state. And we want to model our materials problem onto that, so that we can essentially find the ground state almost free of charge. We'll see. So we want to exploit the current advances here of this simulated annealing process, the ability to all states by evaluating them and typically locate the ground state. And what I want to do is crystal structure prediction, where I'm trying to minimize the energy as a function of particles, or minimize the energy as a function of occupancy. What I mean by occupancy here, so we're looking at a solid solution. I might know the structure of AO and the structure of BO, but what I don't know is the pattern of the A's and B's if I have a mixed solution. Now, there's ways you can do that classically. You have a very, very large supercell. That's a random configuration. You can go for a very small unit cell and do averaging. It's being field. But what we tend to do is we want to reduce temperature is to take a medium-sized unit cell, the largest we can cope with, and look at every single combination and calculate the free energy. As you can see, there's a problem here. There's many, many states. I didn't put the number. That's 100 factorial divided by 50 factorial, 50 factorial. That's a big number of calculations. But what we want to do is use the quantum computers to find the lowest energy configurations for us, so we don't have to compute all of them. The other example is structure prediction. People know that I like to predict the structure of clusters. We're now at A, B, N, where N is the number of forwarded units. The reason I want to do that is because if bulks go down to smaller sizes, the bulk pattern changes dramatically, and every time we change the forward unit, so the structure, so the property. And of course, you can mix these two ideas. You can do solid solutions of clusters, and different properties when you know that. This is how light interacts with these little particles. Any final results like you get red shift and blue shift in photoluminescence when you take zinc oxide and you don't get cadmium or magnesium. But let's get back to what I'm supposed to talk about, and that's using a quantum computer, structure prediction. This is the slide I had a moment ago. I want to basically minimize the number of configurations to evaluate, and I want to have a computational cost of each evaluation to be reduced as small as possible. The questions you might ask is how to generate configurations, how to re-evaluate in the same configuration, how to determine the target configuration span. We believe that's going to be the quantum computer for us. And also the computational cost. What we do classically, we switch, we tend to use interval potentials, and then hope that we can then take the best ones and then do our more quality, expensive and more quality calculations using DFT. And we're going to do something similar with the quantum computer. You have a cheaper cost function to evaluate, and then hopefully you'll find the lowest energy configuration that you move to the second stage. And here is the classical one I was talking about earlier. I'm looking at predicting clusters, and I'm plotting their DFT energy with respect to what rank it was found as local minima on classical using interval potentials. And you can see there's many, many different configurations where you go down different sizes. And I just want to find these down here, because if I find these, then these, when I go to the more expensive energy landscape, which is FHIAs here, I'll just put it into PV Sol. If I find them, then basically I found my answer, I don't need to find the others. So that's what I'm going to try and do. So the quantum algorithm. Okay, so it's global optimization. It uses Kubo as the cost function, so it's a bit cheaper than using DFT, but we're going to fit our parameters today using DFT. Classically, you couldn't see, by the way, the blue energy landscape. There's the energy landscape, a pictorial, simple model. You're walking across this energy landscape, you discover what you find as you're walking. That's classically. What we're doing quantum mechanically is basically all states exist, and as we evolve over time, that little blue, that purple thing is the probability of finding that particular state. It merges into just one state, and that's then given to you. You then convert to what that answer is, and that's your answer. So, how does that work? So, let's have a look. Our first system we look at is graphene. So, vacancies and graphene is what we looked at. We want to know if we've got so many graphene vacancies, what's the pattern that would form that unit cell? And so, how's that done? Here's the unit cell. We number the atoms. 1, 2, can't remember how many there is there. That looks like 8. Okay, we actually use a larger supercell. So there's your site. So you map each site onto a qubit, and then you have to have an energy interaction between these. There's a Kubo formula down there. And here, for this simple model, we'll just say that if an atom is next to another atom, then the energy goes down by -1. In other words, there's a bond. The more bonds there are, then obviously the lower the structure. And when you run your Kubo model, your quantum annealer, then essentially it comes back with 1s and 0s. 0s meaning it's not occupied, it's empty. 1 means the site is in fact occupied by a carbon atom. So that's how it works, that's the idea. And if you do this, well, how does it map? Well, basically, every atom needs to know what its neighbour atom is doing, and you have to form a connectivity tree, which looks like that on the left-hand side, if you look at it. And mapping that to a quantum computer, then each of the qubits we've got now highlighted in blue, and they're connected, if you can see, I don't know if you can actually see, but there are lines connecting these blue dots, and that magnetic strength is basically the Kubo energy terms that's in there that determines how these qubits are interacting. You run it, it comes back with your 0s and 1s. So what we want to do is look at maybe, for example, 3 vacancy structures, and here is the answer that's come out of the quantum annealer. And you can see that with 3 vacancies, the more broken bonds there are, the worse the energy. So it predicts that A is the answer we're looking for. But to do this, of course, we have to have a constraint. Because if you didn't have a constraint on how many vacancies you've got, then basically you'll come back and say every site is still by nitrogen. Sorry, by carbon, sorry. And that's no good, because we know that's the answer to that. We want to know 3 vacancies. So if you add constraints, then unfortunately it increases the expense. And the reason for that is this model here now, you see the connectivity. Every atom needs to know where every other atom is occupied or not. And so there's lots of connections now between all these sites. And when you map that onto your quantum computer, you'll see there's not enough neighbouring qubits, so you have to have more than one qubit representing a site and have a strong field between those, and then you hope that when you find an answer, every site all has ones or zeros, otherwise what is known as a broken bond, broken chain. So that tells you that the number of qubits you need is not just dependent on the number of atoms, but how they interact. And that's the problem here that we need to try and reduce. So how does it all work? Basically, when you run it, you end up with ones and zeros coming out. We've got a few scripts to try and bring together all those equivalents, and we run it, say, here 1,000 times, and you get your results out, it tells you your answer. I've had a notification, I must move on quickly. So let's move on. How well did it do? On this picture here, this framework, you can see, I don't have a pointer, so I'll just point it here. You can see here the energies that are coming out of the QO model. It matches quite nicely in terms of order, in terms of DFT, but only with your single point. When you start optimizing the structure, because the quantum annealer can't optimize the structure only with a single point, so you find there's some structures that are not so great. I'm pointing them out here, but we're not too worried about the ordering of those because they collapse to the ground state. So the quantum annealer is still telling us what's the best ones. We can ignore the higher energy ones, but there is a problem underlying here, and that's the quantum computer can't predict the relaxed structures, but only the structures that are pre-relaxed as well. So what are we currently doing? What we're currently looking at? We are looking at nitrogen Ndau graphene, we're looking at solid solution of gallium nitride, and also a metallic alloy to show that we can also now include temperature and see what's happening. So in this picture here you can see we've added temperature to one of these systems, and we can predict that the amount of nitrogen or the amount of doping that's happening varies quite nicely with temperature. And hopefully this work will be able to published in the next month, so you can read about that later. I should point out that I'm not the only group in the UK that's using a quantum annealer to do structure prediction. There's also a group in Liverpool. They're doing something very similar, I guess. There's the classical bits, there's the energy landscape, and they're sort of moving across the landscape to try and find the global which is dark blue. And what they're doing is they're using discrete points that are evenly spaced across the landscape, and they're hoping that the quantum annealer will find the star quite happily, and that the star basically, when you take that point, will locally optimize to the blue. So it's the same idea that we're using, that you're hoping that the quantum annealer finds the, filters out and finds the good starting point, that when you use your DFT energy function and classical computer now, you can optimize and find the state you're after. And there's more slides on this, but I don't want to go through this. It's not, I'm probably out of time. Chair's going to be nodding. But you can see that the QO model includes the type element there is. You can see the grid spacing here. Every grid point is in the QO model, whether it's occupied and what the type of element there is. Here's a bit more of the details, but the systems they've looked at was given here. They found that the grid spacing about 0.6, 0.7 angstrom difference with grid points, and they're quite happily fine with symmetry switched on to reduce the number of qubits, the structure of perovskites, biolexite, and the pyrofluor structure. If you want to know more about their work, they have a Nature paper there, 6/19/2003. So that leads me to finish by just sending my acknowledgements. Most of the work that I showed basically is the work of Bruno Calvino, who's my RSC, my research software engineer, currently working on the QBAC project. I also have another RSC here today, who somewhere in the audience. He has a poster at the back of the main lecture theatre looking at lithiating manganese oxide materials. I'm also hoping that next year the entire height, or many as I can get to come here, we'd like to have a break-off session maybe on the pre-day and show what we're trying to do, what we've achieved in the PAX project. We have literally 10 members of staff working, RSCs working on different aspects. I'd love to bring them all out here so you can learn what we've learned and whether we're ready for exascale. I do also have, as it says there, if you're interested, I do have, oh, it's in my pocket. If you're interested in the PAX project, I have some leaflets that you can take if you would like one. I've also got some free erasers. In the UK we call them rubbers, but I was told that America is very rude, so I'll call them erasers here just in case. I've got some free merchandise erasers that you can also grab off of me if you're interested. That's there. And that leads me to say, well, that's all, there's a paper. That paper there is just a tutorial, so if you really want to understand how to run the quantum meter and doing a materials application, that's a tutorial paper, so it should be very easy to read. The QR code is just the scripts that we use to take the output of the quantum annealer and make it easier for us to interpret. And there's just the funding people, UKRI, Excalibur, EPSA, and of course I'm also the lead of the MCC, and I think I'm out of time. Thank you for listening, and thanks also for allowing me